Thank you, and thanks for inviting me. This is joint work with my friend and co-author Sungja Du. So this paper is about auction design with interdependent values, basically. And the structure of the talk is a very quick review of the standard classical theory of optimal auctions. And then I'm going to describe to you a new theory we have of informationally robust optimal auction design. And then at the end, if there's time, I'll discuss some applications. Okay, so here's the basic setting. There's a single unit of a good for sale and n risk-neutral bidders with the usual quasi-linear utility. And bidder i's value is VI, and in a finite set, capital VI. And then big V is the set of profiles of values of the bidders. And there's a joint distribution of values mu. And you should think of this as being held fixed throughout the analysis. So we know what the distribution is of the bidders' values, and that pins down the potential surplus that could be generated from the sale of the good. The seller, who's designing the mechanism, wants to maximize expected revenue. And the question is, what mechanism should the seller use? That is, what action should the bidders be allowed to take? And what should be the rules for who gets the good and who pays what, depending on the actions taken by the bidders. Okay, so of course, this model isn't fully specified yet, because first I have to say, what do the bidders know about the values? A standard assumption would be, or a common assumption would be, that bidders know their own value, but don't know anything else about others' values. That would be the private value model. But I want to think more generally about bidders having partial and differential information about everybody's values. So the way we're going to model that is with Harsanyi type spaces, or I'm going to call them information structures in this talk, common prior information structures. So what is a common prior information structure? Well, each bidder is going to get a signal, as little si, and that's in a set big Si. And there's a joint distribution over all of the bidders' signals, okay? And that's going to be denoted pi. And then there's correlation between the signals and the values. And that's described by this function here. It's an interim expectation of the value profile given everybody's signals. Okay, so this W function is like the value function. And this all has to be compatible with the prior mu over values, in the sense that the law of iterated expectations is satisfied if the distribution of this W is a mean preserving contraction of V distributed according to mu. Okay, so as I was saying, an example would be private values, where your signal is just equal to your value. And in that case, your interim expectation, given everybody's signals of your value, is just going to be your signal. And then if you further assume that the values are independent, you'd be back to the independent private value model of Vickrey. But I also want to think about other models, like, for example, the mineral rights model, which would be where everybody has the same value. And SI is equal to VI plus epsilon I, where epsilon I is like a noise term, or is equal to just V plus epsilon I, where epsilon I is a noise term that's conditionally independent across bidders. That would be the mineral rights model. So those are nested within this framework. Okay, so we have to specify the model of information. We also have to say, how are the bidders going to behave? And we're going to employ the standard solution concept of Nash equilibrium. Of course, for a given information structure and mechanism, there could be more than one equilibrium. And the standard assumption is that the seller gets to pick their preferred equilibrium. Okay, so given that, the optimal auction design problem is, given an information structure, choose the mechanism and the equilibrium to maximize expected revenue. And importantly, the optimal mechanism depends on the particular information structure. And I'm going to call optimized revenue on a particular information structure, that information structure's revenue potential. Okay, this is what you could potentially achieve if you could pick any mechanism you wanted as a seller, any equilibrium you wanted. Just as a brief aside, I'm going to use the words auction and mechanism basically interchangeably. Okay.
Ben, can I ask a question?
Please.
About the solution concept. So are you referring to ex post equilibrium? Is it ex post
Nope.
Truth.
I just mean a Nash equilibrium. So of the normal form, where you pick a strategy that maps your signal into an action, a distribution over actions in the mechanism. So this is with the usual interim incentive compatibility. Conditional on my signal, my strategy has to be optimal.
But knowing the distribution over signals of the others, or it is
Correct. And the strategies
so
that they're using.
Bayesian Nash equilibrium.
Exactly.
Okay.
Bayes Nash equilibrium.
Good.
Which I always think of as just Nash equilibrium of a Bayesian game, where your action is a behavioral strategy that maps your signals into distributions over actions. Okay, so here is my artist's impression of the optimal auction design problem. And, here's where I'm showing you all why I became an economist rather than an artist, obviously. So to specify the game, you have to choose a mechanism, and there's some space of mechanisms that you could, or universe of mechanisms, class of mechanisms that you could potentially choose from. And then you have to choose an information structure as well. For a given choice of those two, now we have a Bayesian game, and there are strategies that sort of link the information structure to action, signals in the information structure to actions taken in the mechanism. Some of those strategies are going to be equilibria. There could be more than one. And in the optimal auction design problem, where we're trying to achieve this revenue potential on a given information structure, we could think of revenue on that information structure being increasing in this direction. There are all sorts of different mechanisms that the seller could choose. For each one, there are going to be potentially lots of equilibria, and we're going to be selecting, this should be a mechanism, that and equilibrium that maximize revenue on this information structure. Okay, so that's what it looks like to achieve the revenue potential. And of course, a fundamental result. So this seems like a mind-bogglingly complex problem, because you have to look over all mechanisms and all equilibria. And even for a given mechanism and information structure, finding the equilibria can be a monumental task. But Roger Myerson taught us all long ago that there's a revelation principle here. It's without loss of generality to restrict attention to mechanisms where the bidders just report their signals, and in equilibrium, they report truthfully, meaning that you can use incentive compatible and individually rational direct mechanisms. And to preempt a question Michal might have, here I mean interim IR. So conditional on my signal, my expected surplus in the mechanism is non-negative. So this vastly reduces the complexity of computing the revenue potential and optimal mechanisms, but it does depend on the seller being able to pick any mechanism they want and selecting their preferred equilibrium. Okay, Roger also proved, in addition to the revelation principle, Roger proved this revenue equivalence result, which says that expected revenue can actually be computed using only local incentive constraints in benchmark cases in the independent private value model. And then expected revenue is just an expected virtual value of the bidder who gets allocated the good. Okay, so in the IPV case, we can solve for the optimal auction. In the symmetric and regular case, they're first and second price auctions with reserve prices. Beyond IPV, my opinion, which is of course highly subjective, is that the theory is less tractable and less insightful. So if you have interdependent values, or if you have correlation, the pattern of binding constraints can be quite complicated. The optimal allocation can depend on fine details of the information structure. When signals are correlated, the revenue equivalence result fails. And many authors, including Roger in his original paper, have shown that you get full surplus extraction. Later authors showed senses in which that's generic. And this full surplus extraction is achieved by rather exotic mechanisms that don't seem very helpful from an applied auction theory perspective. Okay. So, I would say that the rules of the mechanism often have a very concrete connection to real world institutions. We can identify the action, the amount that you bid, with how much you tell the seller of a house you're willing to pay for their house, or, what the current price is when you raise your hand, when you're bidding at an open bid auction. The information structure is more of a metaphor. The values and the signals may be related to real world, things in the real world, but the signal is not something that you can necessarily easily measure. It's probably best viewed as something that exists in the minds of the bidders as an as-if description of their behavior. Okay, but that suggests that we should be concerned about misspecification of the information structure, especially because the optimal auction is very sensitive to what we assume about the structure of information. And we don't have a good theory of how a mechanism that's optimal in one information structure would perform if you just plop it down with a different information structure. Okay, so the informationally robust approach that I'm going to talk about today is, instead of considering behavior in a particular information structure, take a more holistic view of mechanism design across lots of information structures. In particular, okay, so there are two things that you could do in that vein. One is, rather than looking at the revenue potential in a particular information structure, look at how this revenue potential varies across information. That's one thing that we're going to be interested in. But another question is, well, what if we fix a mechanism? How would that mechanism, rather than thinking about mechanisms that are optimal for a particular information structure, I want to think about how a given mechanism would perform as I vary the information structure and the equilibrium, and look across lots of information structures and equilibria. So let me define a concept which is a dual, in a sense, to the revenue potential. Revenue potential is fixing an information structure and maximizing expected revenue. Revenue guarantee is when we fix a mechanism and look at minimum expected revenue across all information structures and equilibria. Okay, so the first thought you might have is, well, this number is going to be zero, because what if all the bidders' values for the good are just zero? Okay, but remember that we're fixing a distribution of the bidders' values, okay, when we vary information. So the fundamentals are staying the same, the fundamental value of the good. What we're just varying is what the bidders know about the value and what their equilibrium strategies are in the mechanism. So in general, this revenue guarantee might be non-trivial.
And sorry, so even second price auction have this weird equilibria with revenue zero, right? So if you optimize over equilibria, you will get very low revenue, right?
That's correct. So a second price auction has the bidding ring equilibria where one bidder bids an astronomical amount and everyone else bids zero. So that mechanism would have a trivial revenue guarantee, but the first price auction has a non-trivial guarantee. And that's a result of Bergerman, Brooks, and Morris, 2017, who actually compute the revenue guarantee of the first price auction. Okay. So back to my artist's impression, now we could think about fixing a mechanism, and let's think about on this axis over here is revenue on this mechanism as we vary the information structure and also the equilibrium. Okay. We could look at how this mechanism, what would happen on this mechanism on lots of different information structures. On each one, there could be lots of equilibria. And to compute the revenue guarantee, we're going to select the information structure and the equilibrium that minimize expected revenue. Okay. So there are two problems in this informationally robust auction design agenda that I'm going to focus on today. One is I'm going to call the min-p problem, which is computing the information structure that minimizes the revenue potential. So this is like finding the models of information that are the most challenging for the seller from a revenue extraction perspective. And the other problem I'll call max G is computing mechanisms that maximize the revenue guarantee. So these are mechanisms that are sort of the most robust to the information and the equilibrium in terms of revenue generated. Okay, so do those problems make sense, by the way? Yeah, I guess so. So no questions. All right. So my Songza and I have been thinking about these two problems for a long time, and we wrote another paper that preceded this one on the special case of common values. So common values means V1 equals V2 equals ... equals Vn. So it's obviously a very, very special case of the model. And we showed in that paper that actually the max guarantee is equal to the min potential. Okay, the values of these two problems coincide. And that means that the seller does just as well in the worst case across information, whether or not they can pick the equilibrium and whether or not they know the information structure before choosing the mechanism. We constructed a kind of saddle point for this problem, which is a pair of a guarantee maximizing mechanism, M star, and a potential minimizing information structure, I star. And these certify one another as unimprovable in the sense that, you know, this mechanism it has a lower bound on revenue, that's actually optimal revenue at this information structure. So there can't be another information structure where the revenue potential is lower. And similarly, the revenue potential of this information structure is equal to the revenue guarantee of the mechanism. And so there's no other mechanism that can achieve a higher revenue guarantee. Otherwise, it would have to have higher expected revenue on this particular information structure. Okay. Also, it turns out that there's a ton of structure at the saddle point. In particular, you know, you might have thought that, oh, sure, you know, of course, these are going to coincide because I could run a crazy mechanism where I just ask the bidders to report the information structure, and then based on what they report the information to be, then run an optimal auction, something like that. That's not what happens at the saddle point. Actually, the signals and the actions you could think of as they're linearly ordered. So you could think of them as non-negative real numbers, and the signals turn out to be independent, and all of the arguments about the mechanism and the information structure involve only local constraints. So in that sense, the model kind of reduces to very classical arguments about virtual values and a new concept that I'll talk about in a minute, which is a counterpart to virtual value for the revenue guarantee for the max G problem. Okay, and then the other thing that's especially interesting about the common value case is that the mechanisms that maximize the guarantee are this kind of interesting class of what we call proportional auctions. So the proportional auctions, everybody bids a non-negative real number. As a function of the sum of the bids, there's going to be a total supply of the good and a total transfer. And then each bidder's individual allocation and transfer are proportional to their actions. So this is a pretty low dimensional class of mechanisms that seem like they could be useful for, you know, in an applied setting. Another interesting result about the common value case is if you hold fixed the distribution of the common value and take the number of bidders going to infinity, then in the limit, the max guarantee converges to the expected surplus. So in that sense, when there are common values and the number of bidders is large, there is no loss of demanding informational robustness in the sense of maximizing the revenue guarantee relative to a Bayesian criterion. So I want to emphasize the fact that in this earlier paper, we constructed the saddle point. Okay, so the arguments were very constructive, and honestly, it was a little bit mysterious why all of this worked out. And the question is, you know, is this general? You know, what is the underlying structure of the problem that leads to the max guarantee and the min potential coinciding? Okay. So just to visualize what this solution looks like, it's a pair of a max guarantee mechanism and a min potential information structure, and then there's their equilibria that tie them together. And if you were to hold fixed this information structure and vary the mechanism, then all of the equilibria, as you vary the mechanism, would have lower revenue than this mechanism and this equilibrium. And similarly, if you hold fixed the mechanism and you were to vary the information in the equilibrium, revenue would only go up. Okay. So this paper is basically about explaining the mystery, or at least shedding a little bit more light on the mystery of why the max guarantee and the min potential coincide in a more general set of environments with correlated values. So first and foremost, relaxing the common value hypothesis, allowing for asymmetric distributions of values. And then we do other things as well, like, for example, generalizing to multiple goods with additive values, adding certain kinds of constraints on the allocation, and showing that this max guarantee equals min potential result goes through, and also showing the existence saddle points of that form in an approximate sense that have a lot of the same structure. There's also a dimension reduction result, which is kind of analogous to, you can think of as analogous to a combination of the revenue, of the revelation principle and the revenue equivalence result, which is that it's without loss of generality to restrict attention to actions and signals that are linearly ordered, independent signals in the case of the information structure, and also all of the arguments about you can compute the optimal revenue guarantee and the optimal revenue potential using only local incentive constraints. So that's something that generalizes beyond the common value case. And also a significant result is that you can, so these are really these are nonlinear programs, because for a given mechanism, the set of equilibrium outcomes that you can achieve across information structures and equilibria, that's like it's like a bilinear program, because you have an interaction between the rules of the mechanism and the distribution of signals in the information structure. But it turns out that you can restrict the min-p and max-g programs into linear programs that have the same value. And these bounding linear programs that we construct have a very natural structure. So for example, the min-p bounding program looks like restrict yourself to information structures with a fixed distribution of signals, marginal distribution of signals that's independent, and choose the correlation structure between signals and values in order to minimize an expected highest virtual value. So the min-p program reduces to minimizing an expected highest virtual value, essentially. And on the max-g side, the bounding program there reduces to picking the mechanism to maximize an expected minimum virtual profit, where virtual profit is kind of a dual concept to the virtual value that we introduced in this paper. And then the last thing I'll emphasize is that all of the arguments in this new paper are non-constructive. So they're really showing how the structure of these two problems is related, and why they have the same value, actually. And in fact, what we show is that these two programs are a dual pair in the sense of linear programming in an approximate sense. Okay, and then there are a bunch of applications of the theory. So, one is to the common values case that I was just describing. We have another paper that looks at the case where each bidder's expected value, but you don't know the information structure and you don't know the correlation between values. In this paper, we have a new application where you know the average value of the bidders, but you don't know what the difference is between the values. And then, revenue is used in some of our arguments. It's not particularly important. There's the bounding programs can be generalized to other problems that are not just the allocation problem with revenue maximization. Our result that the max guarantee is equal to the min potential uses revenue maximization, for example, but the methodology seems applicable more widely. And for example, we have a new paper, which is currently being written up on bilateral trade, where now the objective is not to maximize a revenue guarantee, but to maximize a guarantee on the gains from trade between the buyer and seller. And what are mechanisms for bilateral trade that optimize that welfare guarantee? Okay, so there's a lot of related research, and the seminar is already about half over, so I'm not going to talk about a lot of it. But one thing that I do want to emphasize, especially for this audience, is sort of how I see the connection between this work and algorithmic game theory and algorithmic mechanism design. And obviously, the desire for robustness and looking at how institutions would perform in lots of different environments is a common theme. I would say, key difference is, we're using basically a max-min criterion here, maximizing minimum revenue across, maximizing over mechanisms, minimum revenue over all equilibrium information structures. And we're going to compute that exactly whereas, more common methodology in algorithmic mechanism design would be to look for constant factor approximations of the target, optimal revenue. And also another difference is that the emphasis here is on interdependent values and on rich information, whereas at least, from my reading of the algorithmic mechanism design game theory literatures, there's more, people tend to more look at private value information structures or relatively simple fixed models of information. So that's a key difference. Okay, so that was my introduction, which is 50% of the seminar. And now I'm going to describe in a little more detail, what the model is and what these bounding programs are and how they're related. So as I said before, there's a single unit of a good for sale, fixed set of bidders. Each bidder has finitely many values, which is kind of for technical reasons. We did not assume that in the common value paper, but we're going to assume it here so that everything is done with finite dimensional linear programs. And then there's this fixed prior mu. And for technical purposes, we're going to assume that the prior has full support, but we really don't think that this is essential to the result. We have plenty of numerical examples where this assumption fails. It fails in the common value case, but the max guarantee is still equal to the min potential. So a mechanism is a triple of a space of actions for the bidders. This is a product set of actions. An allocation rule, which says as a function of the action profile, what is the probability that each bidder gets the good, subject to a feasibility constraint. And then a transfer rule, which says as a function of the profile of actions, what is each bidder's net payment to the seller. We want to impose a participation constraint. And a usual way of doing that would be to say bidder surplus has to be non-negative in equilibrium. But of course, in what equilibrium? And in what information structure? So our way of modeling participation in a way that's prior free is to say that there's an action that a player could take that would guarantee them a non-negative surplus ex post, regardless of what actions others take. Okay, so this is sort of between an interim and an ex post participation constraint, because this might not be the action that a player takes in equilibrium. Okay, so it might be that their surplus is negative ex post for whatever action they take, but they always have the option of switching to this mechanism that would give them a non-negative surplus ex post. So we're going to look at participation secure mechanisms, and this calligraphic M is the set of those objects. And it's a set because these are finite. We're only looking at finite mechanisms here. An information structure is a pair of signals and a sigma. So sigma, I'm going to model it slightly differently from what I described in the introduction. Sigma is the joint distribution of signals and values, such that the marginal on values is mu, the given prior. And again, these signal sets are finite, so calligraphic I is a well-defined set of information structures. Okay, so given a pair of a mechanism and an information structure, behavioral strategies for bidder I map their signals into distributions over actions. Big B of MI is the set of Bayes-Nash equilibria, and induced profit from the mechanism, information structure, and strategies is just the expected sum of the transfers across all value signals and actions. So here is the max G problem. It's the soup over all mechanisms of the infimum over information structures, inf over equilibria of expected revenue. And this inner problem, the double inf, is the revenue guarantee for the mechanism chosen on the outside. The min potential problem is take the inf over information structures of the soup over mechanisms and the soup over equilibria of expected revenue. So this inner double soup is the revenue potential on an information structure. And I want to emphasize that, of course, this looks sort of like a zero-sum game where we're just comparing max-min versus min-max. But a key difference is that on the inside, in the two problems, we're switching how we're picking the equilibrium. The equilibrium selection rule in the max G problem is to pick the worst equilibrium for the seller. Whereas in the min-p problem, we're picking the best equilibrium for the seller. Okay, so that's an important difference that makes this unlike a standard zero-sum game with a fixed objective. Okay, so these two programs bound how well the seller can do uniformly across information structures for different assumptions about equilibrium selection and different assumptions about whether the seller can directly condition on the information structure when they pick the mechanism. Okay, so I'm going to describe to you these bounding programs now before I state the theorem, and then the theorem will be stated in terms of those bounding programs. And I'm going to start with this min-p problem, the problem of computing the information structure that minimizes the revenue potential. Okay, so if you look at this inner problem is the standard auction design problem. It's pick a mechanism in equilibrium to maximize expected revenue, and participation constraints are sort of cooked in here through the participation security condition on mechanisms. Okay, so of course I could just apply the revelation principle and instead optimize over direct mechanisms that are incentive compatible and individually rational. Okay, and I'm going to do that. Okay, so and you can really think of that inner double soup as just a max. Right, that's just a linear program over IC and IR direct mechanisms. So I want to get an upper bound on this min-p program, and there are kind of two ways. And the way I'm going to do it is by restricting the program, restricting the set of solutions that I can use in the outer inf. And one way you could do that is by restricting the information structures that you're allowed to use. Okay. And another way of doing it is by relaxing that inner problem by allowing the seller to use even more mechanisms beyond just the ones that are IC and IR. Okay. And how could you do that? Well, you could just drop some equilibrium constraints or some participation constraints. Okay, as in the Myersonian upper bound in the revenue equivalence theorem. So we do both. Okay. We do both. We restrict attention to information structures where signals are independent. And we also fix an essentially arbitrary order on the signals, because the signals live in an abstract space. They could just be any finite set. But we fix an order, and then we drop all of the equilibrium constraints, except those that are associated with local downward deviations. And we drop all the participation constraints except for the lowest type. So this is kind of the usual Myersonian relaxation, but we're just kind of pulling it out of thin air because there is no inherent order on how the signals are related to values. Okay, in the Myersonian world, your signal is your value, and there's some single crossing and preferences, which kind of suggests that that's the right relaxation. Here, we're just doing it without even knowing what the correlation structure is between signals and values. Okay, so this min-p problem then reduces to choosing the correlation structure between signals and values to minimize an expected highest virtual value. So let me establish a little bit more notation so I can show you exactly what that means. We're going to look at information structures where the signals are in a grid, where the grid is indexed by a k, and k is the highest signal in the grid, and the grid has signals in increments of 1 over k. Okay, so we're just going to have the whole signal space is just the product of the n-fold product of these grids. So when k is large, when k is large, the marginal distribution on the signals is basically a normalization, because I could always, instead of telling you your signal, I could tell you what the quantile was of your signal, and it would have exactly the same information. So the marginal distribution of the signals doesn't really matter. We can pick it to be whatever we want. And it turns out that a particularly useful normalization for the marginal distribution on signals is a censored geometric with arrival rate of 1 over k. So this is the functional form for the censored geometric. It's not important for you to know what that functional form is. You should think of it as the discrete approximation of an exponential distribution. Okay, so this distribution is going to converge to exponential on R plus with an arrival rate of 1 as k goes to infinity, converges in distribution. And of course, the signals are independent across bidders. Okay, so a little bit more notation. I'm looking at this grid, and I have a function on this grid that maps into Rn. So this is a vector field. And I'm going to define a discrete upward derivative, which is denoted by this. So this is the difference between the ith coordinate of the function if I increment the ith argument by 1 over k, and then scaled up by a factor of k minus 1. And usually you would say, well, shouldn't this be k? Shouldn't I be scaling up by k, 1 over the increment? And I should. Obviously, k and k minus 1 are basically the same when k is large. It turns out that k minus 1 is much more convenient for our calculations. And I want to be honest with you about exactly how it's defined in the paper. Okay, this is the vector of these own discrete derivatives. And this is the discrete analog of the divergence, upward divergence, the sum of these own derivatives. Okay, so here is the bounding program for min potential. Okay, so first I'm going to take a min, and the min is over information structures. It's over joint distributions of signals and values, where the signals are in this grid, and this is the space of values, such that if I take the marginal over values, that coincides with mu. And if I take the marginal over signals, that coincides with rho, this normalization of the signal distribution that I described 2 slides ago. Okay, so that's what I'm minimizing over. This W is basically just introduced for notational convenience, is the interim expected value. So this is saying conditional on everybody's signals, on the profile of signals being X, this is the expectation of the value profile. And then what is the actual objective? The objective is going to be minimizing the sum of a collection of upper bounds on revenue as a function of the signal profile. And I'm calling those gamma. So gamma of X is an upper bound on revenue when the signal profile is X. And gamma of X has to be greater than or equal to this expression here, gamma over rho. This is basically a virtual value. This is basically a virtual value. And let me explain to you why. So we're all familiar with this formula for the virtual value in the independent private value case. Now, if I went to interdependent values, and this is like the social value of allocating the good to bidder I, this is some cost, a measure of the cost of incentives or the information rents that bidders accrue when this type gets allocated the good. If I went to interdependent values, I would still have social value of allocating to bidder I, which is now the interim expected social value conditional on the profile of signals, minus a similar hazard rate, inverse hazard rate. But now it depends on the signal distribution. Remember, in the independent private value model, the signal is equal to the value. And then I have to add another term, which is the sensitivity. The sensitivity of bidder I's value to bidder I's signal. Okay. Now this is 1 when your value is equal to your signal, right? And of course, there has to be a term like this, because what if my signal doesn't affect my value at all? Then I have no information, basically, and I should not be getting an information rent. Okay, so this is the generalized formula that appears in, say, Bulow and Klemperer, I know how to write a K, 1996, in their appendix. And now if I specialize it to this case, I basically picked the censored geometric so that this is equal to 1. That was the purpose of that normalization, was so that this hazard rate would drop out. You know, in the limit, the exponential distribution has a constant hazard rate equal to the arrival rate. And then all I'm left with is this term and this term, which is exactly what I have down here in their discrete analogs. Does that make sense? So this is the analog of the virtual value, and this whole bounding program corresponds to choosing the information structure to minimize an expected highest virtual value. Now, on the max guarantee problem, I can do something very analogous. So with the max guarantee problem, I'm doing a max over mechanisms, and then a double inf over information and equilibria of expected revenue. And I can look at this inner problem, and I can apply a revelation principle for information design. And instead of optimizing over information structures and equilibria, I can optimize over Bayes correlated equilibria, which is this incomplete information generalization of correlated equilibrium that was proposed by Dirk Bergman and Stephen Morris in 2013, 2016 papers. Okay, and these Bayes correlated equilibria, you could think of them as information structures where your signal is an action, and in equilibrium, the bidders obey their recommended actions that they drew from the information structure. Very much analogous to how the revelation principle for mechanism design is. I mean, direct mechanisms, your action is your signal, and you report truthfully your signal. Okay, so if you do that, that inner double inf problem basically becomes a linear program. And we restrict this problem by fixing an order on the actions, an arbitrary order. And in particular, we're going to take the space of actions to be the same grid that we were using before. And we're going to drop all of the non-local obedience constraints in the correlated equilibrium. Okay. Now, the analog of the independent signal censored geometric assumptions that we applied in the min potential problem is basically choosing the Lagrange multiplier on local obedience to have a particular value, which is 1. Okay, and the reason is that in the classical model, there is a close connection between the inverse hazard rate. It depends on how you normalize the incentive constraints, but if you put them in ex-ante units, then this is basically the Lagrange multiplier on local incentive constraints. So if I'm normalizing the inverse hazard rate to be 1, that's like normalizing the Lagrange multiplier on local incentive constraints to be 1. So we're going to do the same thing. So with this restriction, the bounding program for the max guarantee looks like this. Okay, so this is choosing a mechanism, so a Q and a T, an allocation rule and a transfer rule, subject to just feasibility. This is the participation security condition that, and now 0 kind of means 0. The 0 action in this grid is the participation secure action. And this is saying that if you say 0, you don't pay anything. So your ex post surplus is going to be non-negative no matter what your value is. And then what are we maximizing? We're maximizing these lambdas. You should think of lambda as a lower bound on revenue given the value profile. Before we had gammas, which were upper bounds as a function of the signal profile. Now we have lower bounds as a function of the value profile. And the lower bound on revenue, when the value profile is V, has to be less than or equal to, for every X, first of all, revenue at X, and then plus this additional term, which I'll call a kind of strategic adjustment, which incorporates the cost of incentives. In particular, this is the sum of the local change in the bidder's surpluses if they were to increase their actions, increase their reports by 1 increment in the grid. Okay. So we call this virtual profit. And this bounding program for the max guarantee is computing a mechanism that maximizes the expected lowest virtual profit, where lowest is across all, so the expectation is across values and the lowest is across action profiles. So here's the theorem. First of all, these bounding programs are in fact bounding programs. And under this maintained full support assumption, there exists a pi star such that, basically these bounding programs are indexed by a K because I was doing it for a fixed grid, X of K, of actions and signals. But if I take K to infinity, then the values of those restricted programs converges to this number pi star. And therefore, min potential equals max guarantee equals this pi star. Okay. The full support assumption is only needed for this. This result goes through, and in fact, it goes through more generally, as I was saying before. I also want to say that, beyond just helping us to compute this value, the solutions to these programs are approximate potential minimizing information structures and approximate guarantee maximizing mechanisms, in the sense that I can always pick K large so that the value of this program is at least pi star minus epsilon, and the mechanism that comes out of that max guarantee program for that K is going to guarantee revenue of at least pi star minus epsilon in every information structure in equilibrium. So these programs are actually giving us a way to compute approximate optimal information structures and mechanisms. Okay, so I'm kind of running shy on time, but I do want to give you a sense of why are these two programs related? And, as I said before in the introduction, these are almost a dual pair in scare quotes. So what do I mean by that? So these are the two programs. And you can already kind of see that there is a relationship between them. So for example, this lambda has a weight of mu in the objective. Lambda, of course, ends up being the multiplier on this constraint here in the dual pairing, okay? Gamma has a weight of 1. There's only one variable over here that has a non-zero right-hand side, and it's over here. Gamma ends up being the multiplier on this feasibility constraint in the mechanism. The other ones, it's a little hard to see what the connection is. So let me explain how we get to that connection. So we have to do a substitution in this program, basically, to see the rest of the connection. And the tricky thing is, I should say, what does the allocation correspond to? The allocation corresponds to this one down here, actually. The allocation Qi of x is the multiplier on the constraint that the upper bound on revenue has to be at least the virtual value of bidder I. Okay. So it's really the transfer that's a problem. There's nothing to map the transfer into over here. And of course, there's this constraint, and we need to find a multiplier for that one over here. So the way we're going to do that is by replacing the transfer. And you notice all that matters is the difference between the divergence of the transfer and the sum of the transfers. So I'm going to just define a new variable, which is that difference of the divergence of the transfer minus the sum of the transfers. We call this the aggregate excess growth. So we could substitute in this big C for the transfer rule in the max guarantee program, bounding program, but we have to add an extra constraint that there exists a T for which this equation is satisfied. Okay, we can't pick any C, we could only pick C's that could be generated in this way. If you apply the Fredholm alternative to this system of linear equations, and also with this equation down here, you get that for a given C, there exists a T that solves these equations, if and only if the expectation of C under that censored geometric is 0. Okay, no joke. Which is not too surprising because, of course, the censored geometric, that solves a difference equation. We have kind of differences built in here. So it's not too surprising that this would pop out, but it pops out. Okay, so we could just add this constraint into that max guarantee program, or, it turns out an equivalent thing to do is just add the expectation of C into the objective. So if I do it that way, then this is the program that I end up with, which is equivalent to the previous formulation of the restricted max G program. And now you can see what the dual pairing is. C ends up being the multiplier on the marginal distribution of signals, because this is the right-hand side here is the coefficient in the objective. And sigma is actually the multiplier on this constraint down here. Okay, so now these look like almost a dual pair. Let me take the dual of this one. I'm going to show you exactly what it is. It's this right here. They look almost exactly the same, except for one key difference, which is in the program on the right, I have local deviations going up. And in the program on the left, I have local deviations going down. And that's the difference between these two programs. And so the rest of the argument is basically about taking K to infinity and arguing that the solutions to these programs are sufficiently regular that whether you take derivatives going up or down, you're going to get the same answer. Okay. And that's a tricky argument, it turns out, and that's where we use the full support hypothesis. But there's a way to make it work. Okay, and then in the interest of time, I'm gonna skip the detail on exactly how we show that the two programs have approximately the same value. How do you show that there's enough regularity in the solution Q when K is large? Okay, so we think that this virtual profit is kind of neat, and it's a new object that comes out of this analysis. So you should, just as like the virtual value quantifies the potential for revenue extraction subject to incentive constraints, this virtual profit quantifies kind of a mechanism's susceptibility to low revenue from the information and the equilibrium. In particular, what could information do? Information could be used to coordinate the bidder's behavior on action profiles where the virtual profit is low. Okay, so these would be actions where maybe the transfer is low, the sum of the transfers is low, but those other components, the strategic adjustment is relatively high. An informationally robust auction is going to be one that controls this lowest virtual profit, and thereby limits the scope for sort of adverse coordination through information on low virtual profit action profiles. This is something that we haven't developed yet as much as we probably should, but one could really pursue this analogy between virtual profit and the virtual value. For any mechanism, you could compute a lower bound on profit for that mechanism on expected revenue by taking the expectation of the lowest virtual profit. Or more generally, you could formulate an analog of the revenue equivalence result, which says that two mechanisms and equilibria have the same expected revenue if they have if they induce the same virtual profit, meaning they induce the same allocation and the same aggregate excess growth. Okay. But importantly, when you talk about this bound on the guarantee, when you're computing the revenue guarantee of a given mechanism, you can get a lower bound on the revenue guarantee by computing the expected lowest virtual value. But that bound need not be tight. Just like the Myersonian upper bound on revenue doesn't have to be tight. It is tight in the independent private value model and in certain other models, but in general, you could have, you might have to use other constraints, non-local constraints, in order to get a tight upper bound on revenue, as in the non-regular case, where you have to iron the virtual value. Okay, so it turns out that for the max-min auctions, this bound is always tight. The expected minimum virtual value. Okay, so I should show you an actual mechanism at some point in this talk. So a way to operationalize this theory in the way that we have operationalized it in the past is look at special cases and solve these bounding programs for min P and max G, and then looking at the simulations, infer what the functional form is for the guarantee maximizing auctions or mechanisms and the potential minimizing information structures. And then just kind of jump to the continuum limit when K goes to infinity and analytically verify that those functional forms are a settlement. Okay. So let me illustrate how this worked in the common value case. When we wrote this common value paper, we did not know that there was this structure theorem and that the max guarantee in general coincided with the min potential, but we just kind of stumbled across those programs as a crude bound, and they ended up being tight. Okay, so let me describe what the solution looks like. In the min-max information, as I said, those censored geometrics converge to standard exponentials with unit arrival rate. And the worst case information structure is described by a value function that, remember, now all the bidders have the same value because we're in the common value case. And it turns out that the worst case W only depends on the aggregate signal. Okay, why is that? Well, this is the formula for the virtual value under our exponential normalization that makes the hazard rate drop out. And if W only depends on the sum of the signals, then this second term is just going to be the same for every bidder, and it's just W prime. Okay. So in other words, with this functional form, the virtual value is the same for all of the bidders, which is a not too surprising feature of the potential minimizing information structure. It equalizes virtual value so that the seller is indifferent between who they allocate the bid to. There's a little bit more work to pick the exact value function that makes this one as large as possible, makes the expectation of W prime as large as possible, which is what pulls down the expected revenue as much as possible. It ends up being in some cases, it ends up being this sort of fully revealing value function where the common value and the sum of the signals are comonotonic. So the sum of the signals is a sufficient statistic for the value. But more generally, you have to do this procedure that we call grading, which is a way of taking this fully revealing value function and modifying it so that the virtual value is always non-negative and the seller is always willing to allocate the bid rather than withholding it. Okay, here are the proportional auctions that I briefly mentioned in the introduction. So in the proportional auction, again, these actions are non-negative real numbers, and the mechanism is parameterized by two functions, an aggregate allocation and an aggregate transfer rule. And those rules only depend on the sum of the actions of the bidders. And each bidder's individual allocation and individual transfer are just proportional to their actions. Why? Why do you get this proportional form? The reason is that if you compute the virtual profit for these mechanisms, it has this form right here. It's an hour into the talk. I do not expect you to assimilate this formula. There's a key feature of this formula that I want to highlight, which is this. The formula only depends on the value and the sum of the actions, meaning that this mechanism equalizes virtual profit across all action profiles with the same sum of the actions. That's the key feature of the mechanism that's driving its informational robustness, is this equalization of virtual profit across lots of action profiles for a fixed value. Okay. This is the full surplus extraction, asymptotic full surplus extraction result that I was telling you about also in the introduction. In a case where the value is uniform between 0 and 1, the expected value is a half, and the optimal guarantee, which is these purple or these blue stars, converges to 1/2 asymptotically at a rate of 1/n. I should have emphasized that more because this audience especially, I think, would be interested in the rate at which optimal revenue converges to full surplus. All right, I think that's a good time to stop. So there are other applications that we have in the paper, and other kind of interesting optimal informationally robust auctions that we derive. We sort of feel like there's a lot of work to do on this informationally robust auction design problem. One is for getting with these finite approximations, work directly in the continuum limit. We're not good enough analysts to find the right dual pair of function spaces in order to formulate that program yet. An analog of the complementary slackness theorem we think is true. When do you have a saddle point between a guarantee maximizing mechanism and a potential minimizing information structure? We think there is a way of formulating sufficient conditions for that in terms of complementary slackness. Truthful equilibrium at the saddle points, that's something I didn't get to talk about. Exact solutions and other interesting environments. a big thing for us is, as I said before, generalizing the environment, beyond revenue maximization, beyond the single unit allocation problem. The bounding programs generalize quite easily. The tightness result is harder, and some different proof technique is going to be required to show that those two programs have the same value when k is large. And then another thing is, this model, we've gone from one extreme in the standard model where we know the information structure exactly, to another extreme where we don't restrict the information structure at all beyond restricting the distribution of values. And we'd really like to find a way of interpolating between those two extremes with kind of more flexible kinds of restrictions on the information. So that's something that we're working on as well. And that's a good point to stop. So thank you very much.